Okay, good morning, everybody. Welcome to our Friday seminar series here. Today we have the pleasure of having Dr. Obeysekera give us a talk on climate change, re-engineering the practice of engineering. Dr. Obeysekera is the co-director of the Florida Climate Institute. Has many years experience in water management, modeling climate change, and sea level rise. He is the recipient of the prestigious Norman Medal from the American Society of Civil Engineers. So let me turn it over to Dr. Obeysekera. Please go ahead.
Yeah, thank you, David. You can still see my full screen, right?
Yeah.
Okay. So again, good morning, everyone. I'm going to talk about, this catchy name I picked, re-engineering the practice of engineering. Basically, my message is, as you will see, how we need to think about a new paradigm because of the climate change implications, and most of the young engineers that we train, I think, need to think along these lines. Anyway, just this little video that I have, it's from the Miami Beach. I took about 4 or 5 years ago. This is the kind of change we are seeing already. I don't need to go through all that, and you're all familiar with what's happening in Miami Beach. So I don't want to go through a whole lot of details on climate change. I'm sure you're pretty familiar with this, the whole issue of greenhouse gases. And this particular, on the lower right, you will see the greenhouse gas concentration pathways. This United Nations body I call IPCC, they come up with this greenhouse gas pathway. Obviously it's difficult to predict, where we are heading. So they come up with these low scenarios to high scenario. And then that scenario is important for us to understand the implications for instance, the water resources field that I'm involved or some of you are involved. So what I'll be focusing mostly is on water in general, floods and sea level, and maybe precipitation. So in terms of key messages that I'm going to basically communicate is for us to understand climate change is a threat multiplier, and our traditional ways of engineering practice might not be adequate anymore. We need a new paradigm. The other concept here is what I call stationarity is dead. This famous paper that came up in 2008. Whether our infrastructure will survive the kind of traditional practices of engineering. Basically, climate change undermines our basic assumptions, or approaches that we have been using historically. The third point I want to, communicate is that we need to think about planning for future conditions. We always think about the past, but I think we need to think about future condition when we plan. And obviously, future condition is uncertain. And we need to adapt what I coin, this term that I coined called resilient sustainability. We always talk about sustainability. I don't need to go through the definition of that. But basically, now, because of this climate change, we need to make sure that sustainability is resilient going forward. And that's why I call it resilient sustainability. And finally, we also need ways to deal with what we call deep uncertainty, and you will see why we need to worry about that, and this concept of dynamic adaptation. So these are some of the things that I'm going to present today. We already see signs of climate change. Sometimes the climate change is basically a threat multiplier. There's already discussion on Hurricane Ian what part of that is already due to climate change and so forth. So the debate is already ongoing. But we have data on this graphic. You see all these arrows upward are consistent with what you would expect under climate change, with the rising sea level, rising temperature, and the black arrows going down. They're also consistent with the climate change, glaciers melting, ice sheets melting, and there's data behind. And NASA has a nice dashboard showing where we are. You see that little inset of the end of the graphic, carbon dioxide, Arctic ice sheets, and so forth that I routinely look at. We have data at the global scale. You see the atmospheric warming trend compared to the pre-industrial era. It's about 1 or more degrees centigrade increase globally, which is a big amount, relatively speaking. And then the rising sea level that we worry about in our area, in pretty much, which is showing signs of acceleration at the rate of right now about 3.3, 3.4 millimeters per year in the data, basically from the satellite data. In terms of water resources that we worry about, basically we know about the hydrologic cycle, but the concept here is that this hydrologic cycle will basically be accelerating itself. And some people call it's going to be on steroids, because you have more energy coming into the oceans and into the atmosphere. So the hydrologic processes will have more induced energy to in terms of processes, what's happening on land and in ocean. So our interest is in temperature, precipitation, evapotranspiration, and sea level. But I will be focusing on precipitation and sea level and also on floods. And we have its implications are in ecosystems, the human health, the water management, all aspects that we care about, we need to think about. So when you look at this, the landscape, this is a cartoon of, where we are in Miami. You have the coastal areas, highly developed, and interior areas, and the Everglades. And you have these threat multipliers, sea level rise and storm surge. We already saw what happened last couple of days on the West Coast. Saltwater intrusion, that's something we don't talk a lot about. I'll get back to it later. Rising groundwater levels, which is something that's not common in other parts of the state or even the country. So that's something we had worried about here. And the changes in rainfall patterns, particularly the intensities. And obviously the big one is the kind of event that we saw last 2 days. The idea now is these hurricanes will have more frequent major storms going into the future due to climate change, higher rates of rainfall within a particular, within the hurricane itself, and all kinds of, and there are signs of discussion that the hurricanes may also be slowing down, and that's something that we are trying to investigate through some collaboration with the Department of Energy. We are not doing the modeling, but I'm encouraging them to look at that aspect. The other aspect is this compounding effects. As I mentioned, you have the rising sea level, and with that, we know the high tide flooding, the changing heavy rainfall, and rising groundwater. And typically, engineering, we design roads and buildings for various, what we call return period or risk. So the question is, are they sustainable going into the future, or in the future, do we need new criteria for planning and design? We already seen the impacts of climate change. You see these pictures of flood, Fort Lauderdale Airport being flooded, place in Key Largo flooded for 60 days continuous with just from tidal flooding. I mean, it's unprecedented. And obviously the Miami Beach story. And then the other extreme, you also see major droughts, particularly in the Western US. This Lake Mead unprecedented low levels, threatening the water supply even to California and other locations. You see this reservoir, gone down not too long ago. So we have bigger or larger extremes on both sides of the spectrum. And obviously the big one is also flooding, this picture of flooding in Houston, and also these little insets, what you see, what happened in Bangladesh or Pakistan, I don't remember at that. And then obviously some of the other recent flooding in Spain and other areas. So we seem to have these major flooding events. And the question is, are we having more intense rainfall within the events, and has the rainfall runoff processes have they changed? The other aspect is the saltwater intrusion. This is kind of a cross section of, if you take, for example, Miami Beach, you have all these high-rise buildings. The reason I'm saying this is, you all remember what happened in Surfside not too long ago. Now the concern is the saltwater intrusion might be interfering with the integrity of our foundation system, the piles, and the rate of corrosion is increasing. And there has been some suggestions that maybe the corrosion over the years may have weakened the foundation. So we have a new threat in terms of saltwater intrusion that we need to think about in terms of the infrastructure going forward. And these pictures of what happened in that location after the event. So NASA has, I would encourage you to look through this site. They have a wonderful set of tools now for us to look at future projections of sea level rise. There is an interagency sea level rise scenario tool, and I was involved in the report behind this work. Basically, a new set of projections in 2022 that is based on the new IPCC, or Intergovernmental Panel for Climate Change by the United Nations. So they published their projections globally. You see on the right-hand side, and then the NOAA and NASA and other federal agencies got together. And I wrote a use case for this report on how to look at extremes that I will be talking about a little bit later today. So in terms of projection, this particular tool provides projections for any locations. And I just downloaded the Virginia key, which is closest to us. You have these sea level scenarios. You have a broad range of projections. And the reason is that we don't really know how the ice sheets would melt. And I'm not going to go into the background on that. But ice sheet in Greenland and Antarctica play a major role in the future sea level. So you have this range of scenarios that we as planners or engineers, we need to decide what do we plan for out of these scenarios. It's what I call risk-based framing. If you are building or expanding a nuclear power plant, you might want to think about this probably low probability, high magnitude scenario into the future versus if you are building a culvert. So we have these scenarios that we have come up with that people have been asked to use. And in this particular site, you can also look at what are the contributions of different components of sea level rise, whether it's due to the ocean warming or thermal expansion, or is that due to ice sheet or land water storage. So basic contributors to sea level rise, and what components become important depending on the scenario. As you can see, the high scenario it includes a large contribution from places like Antarctica. So anyway, so with this, regionally, we have what we call a climate change compact, and I chaired the sea level committee for this compact, the 4 counties in our region, Palm Beach, Broward, Miami-Dade, and Monroe. They were tired of having these different scenarios from various agencies. They asked us to come up with what we call unified set of scenarios. So we developed these scenarios for local use, and many of the communities are using these. And This was developed in 2019, so they have asked us to revisit that in the light of the new scenarios that have come up with. So basically, we recommended the scenarios that should be planned depending on your design life, how much sea level rise you need to look into. This is the regional mean sea level rise. And depending on your infrastructure type, we gave recommendations on which curve to use. The other aspect that we didn't have to worry about in the past is this tidal frequency. In other words, this time of the year, by the way, next week, in October 9th or 10th, we have what we call Sea Level Solutions Day. We go out and engage the citizens to go out and measure flooding. That's when we have these king tides. And the problem is we are going to have increasing frequency of king tides. And at some point, depending on the scenario, the entire year might, a particular location might be flooded 365 days a year. So that's a concern. And then, I just want to refer you to another wonderful tool from NASA, what they have predicted using some sort of a stochastic approach. How does the number of days of flooding vary with time? You see this for a particular scenario. The nice thing about this tool is you can set your flood threshold. If your elevation, let's say in your location, you can set it up here and see how the flooding changes. Another aspect that this particular research demonstrated is that, after about mid-2030, the rate of flooding, increases significantly. And they attribute this not only to sea level rise, but also this another phenomenon called nodal cycle, which has a 19 years long. So when you are on the sort of the decreasing aspect of nodal cycle, maybe sea level rise is not significant. But when it is, on the rising side of the nodal cycle, it might compound the natural sea level rise, global sea level rise, or regional sea level rise we have. So they attribute this taking off of flooding by mid-2030s due to that nodal cycle phenomenon. I don't have time to go through that right now. So let me go ahead and start talking about the precipitation projections and how we need to think about this future paradigm of planning and projections. So the only way to get precipitation projection is obviously we don't have definite projections like for sea level rise, but we do have projections from climate models. Now, there are a lot of challenges with these climate models I will talk about later on, but basically the idea is the global models of climate simulations are very coarse. These are like 200 of the order of 100, 200 kilometers. I mean, some models on, Florida covers only like two or three grid cells. So we had to do what is known as downscaling. So there are different types of downscaling available, what we call dynamical downscaling, which is a physical modeling to downscale very coarse scale global models down to the scale of interest to us in our area, for example. And then there is also statistical downscaling, basically a general statistical relationship I use to project. We have used both, and I will not go into too much of that today, but I'll give you some examples. But typically, what we have to do, these climate models are we're notoriously unscaled for precipitation as compared to temperature, particularly the extreme rainfall. So we do what we call basically checking these models out. We downscale and then we see during the past century how well these models compare to our observations. And then, we have the observation data. And I think that's an important step, which models are better than others. And then we use it for projections. Just very quickly, a couple of approaches. We have used stochastic modeling of extreme rainfall. You could use the annual maxima. In other words, each year you look at the maxima, let's say sea level or floods, and then in this case, the precipitation, and we do a frequency analysis for this annual maxima. or you do what is known as a peaks over threshold. The problem with annual maxima is, you only have one value per year. So if you have 30, 40 years of data, you only have 40 values for the analysis. But in this case, peaks over particular threshold, you may have a lot more, extremes that will improve your confidence in estimation. So we have used both of these approaches. I won't go through in detail how to do it, but that's certainly an interesting area of research. So the whole concept of precipitation, how do you plan for precipitation, is, we have this depth, duration, frequency curve for precipitation. You plan a project, you have these standardized curves from either NOAA or some other agency or local government. So these have been developed using the historical data, but the question is, under future conditions with the climate change, based on informed by the climate models, how should we adjust these curves? Presumably upward, because you're going to have more intense rainfall in the future under climate change. But how do we come up with those, what we call as increasing the factor to increase these DDF curves into the future? So what we have done here is taken those downscale data sets for large number of stations in Florida and did some analysis for each of the data sets to compute, to do the kind of modeling that I explained earlier, the annual maxima or peaks over threshold, to come up with the DDF curves under future conditions. And more importantly, so when you do that, one of the things that you have to do is what we call bias correction, because you have this is the probability distribution of observed rainfall in blue. In green, actually what the climate model for just show for the same period. Obviously, they are not going to be identical for various reasons that I won't go through. And then you have future conditions. So in this case, the future precipitation is higher than the base condition or observed. So we kind of come up with what is known as a bias correction for this. And at the end result of that is, it gives you what is known as a change factor. In other words, how do I change that observed curve that I showed you a minute ago? How do I adjust those using what we call a change factor? And then I've done this for the entire state, grid scale by grid scale, doing those statistical modeling, and I come up with these contours of change factor for the state. As you can see, the upper part of the state having a higher change factor compared to our area, for example. So this is something I have produced for Florida Department of Transportation as a way for them to maybe adjust their rainfall when they plan or retrofit an existing infrastructure project. So this is how the new sort of the leading concept behind the paradigm of planning for future conditions. Now, Water Management District is also doing something similar, but focusing only on within their own district. So let me go into the floods and sea levels now. How do we adjust for future conditions? So our stationarity approach is what you have learned in school, probably this concept of traditional concept of return period. But in this case, the stationary approach is used. In other words, we assume that the past is an indication of what is going to be happening in the future. So our probability distribution for extremes that I discussed earlier will basically not change with time in the future. So you can use the past and the statistically analyzed data to develop what should my design quantile or flood level should be. This quantity I call CQ0. So this is the stationary approach. It doesn't mean that things will be fixed. It means that the same physical mechanisms that generated the flood in the past will also be prevalent in the future. And it's like past is a key to the future. So this is the concept of return period that the engineers have been using for decades. We all went to school learning this. But now we need a new paradigm, because this is what we have. In the future, typically in many places, you see this changing conditions of extremes, as I mentioned earlier, whether it's due to land use changes or climate change. The extremes are increasing in magnitude. You see the events that we discussed earlier. So in other words, if this particular trend continues, the probability distribution will be shifting up and up. But at time t0, when you have to build a project, you have to decide on a particular design quantile, because you're not going to change your project size with time. So you have to decide on a project size, maybe in 2020 or now, but that would function well into the future under changing conditions. So this is where the non-stationary approach that I'm going to explain will come into play. So the other point I want to make is this return period now is not a fixed quantity, because our exceedance probability keep increasing. And I will show you a graphic on that later on. So the current practice is we take the set of data, we fit a probability distribution, could be extreme value distributions. I don't know if you have had any statistics background where you fit a probability distribution, you come up with the flood quantile or CQ or CT as we denoted for a given return period. You may design your house pad elevation for 100-year flood stage, or your roadway elevation for 10-year flood, or your dam for 500-year flood. That's the traditional approach we have been using. That's the current practice. This graphic explains what it is. Basically our probability distribution doesn't change. This is the fundamental approach we are using. We assume when does the first time the flood will occur. This is kind of the theory behind that, to show that what we call a waiting time distribution. The waiting time is the time we have to wait until the first event occurs. And that obviously is a random quantity, because it could happen the first year, it could happen second year. It may never happen within your lifetime of the project. So, but it could go up to infinity in theory. So that distribution for waiting time is the geometric distribution that I don't have time to explain that, how it's derived, very easy. But the idea is now we use the waiting time as the concept. The reason I'm doing this is it is very easy to continue this concept into non-stationarity situation. And so under stationary condition, we know that our return period is 1 over the exceedance probability, or our risk is equal to this, this risk formula, 1 minus p to the power n. So we know we can design projects based on return period and risk concepts. So now let's think about the non-stationary situation. Our conditions are changing. We have a trend. In this particular case, it's a sea level rise. So your extremes are increasing. Your mean is also increasing. And the point here is that our probability distribution is also being lifted up with time, because there is a trend that presumably will continue. So those sea level rise projections will basically make sure that this goes up and up. So how do we design, for example, the roadbed elevation that's on the coastline, which is our CQ0, or maybe a sizing of a bridge that is out there? So that this non-stationary paradigm is, how do we produce design quantities for this type of change that we are observing? So in that case, I'm not going to go into the theory, a lot of theory behind that. It's basically the same approach that our probability distribution, but now it's a little different. Our parameters are functions of time. Earlier, under stationary situation, our parameters were fixed. And now our parameters are changing, because if you look at this graphic, these probabilities are changing. Some of the parameters are changing with time. For example, location parameter is changing with time or increasing. So that's why we put theta sub t, or the vector of parameters. So in this case, our exceedance probability are also changing with time. PT is 1 minus F as given here. And you can see that the exceedance probabilities are increasing because of this rising trend. And so with this approach, we have come up with formulas for the non-stationary return period that I will show you in a minute. And in a similar manner, we can also develop a risk formula when the probabilities are changing with time. And that's the risk formula. And I will show you in this graphic what those formulas are. So this is the kind of condition you see this graphic. We have an increasing trend in the future under future condition. So we use 3 criteria for future conditions. One is the expected waiting time. Instead of calling a return period, I call it an expected waiting time, because now we have changing probabilities. So this formula provides us, if I know how the probabilities are changing, how to compute my expected waiting time or sort of equivalent return period under non-stationarity. So if the probabilities are increasing, this t value will be smaller. In other words, we will see a failure event sooner than later because our exceedance, our probabilities are increasing in time. And the other approach we have developed is the risk-based approach, changing probability. So you can specify a risk and then develop, what should you design for, which is basically this CQ0. And I've also suggested recurrent flood frequency as a measure of, or as a way of design. The idea behind this is that we know that the frequency of flooding, for example, tidal flooding, will increase in time. So we typically assume in the traditional approach, once our design is exceeded, the project is basically it's going to fail. I mean, like a seawall, it may be, it might fail, but in reality, it might not fail. If we design a project, sort of like an innovative project that we make sure it doesn't fail in once or twice, maybe you can tolerate 3 or 4 floods. Can we use that criteria to come up with perhaps a cheaper design? In other words, assume that it could be reused, and I'll come back to it at the end. So we develop this curve, what I call return period curve. So if you design for 80-year return period, your level of protection is actually only 40 years of expected waiting time because of that non-stationarity. So this is the tool that you could use. If I want to have a 30-year level of protection, it will tell you what you need to design it for today. And the rate of this curve depends on the rate of non-stationarity you have in your process, whether it's sea level rise or flood. So that's the approach. So why should this matter? Because if I design, you see on the left-hand side is for the sea level rise for Key West. On the right-hand side is the Shingle Creek up in the Orlando area. So if you design a project for 100 years under stationarity, we can expect that to have a level of protection of 100 years through time. But under non-stationarity, by about 2040, you only have a 50-year level of protection, or 17 by 2060. So this is that dynamic return period that I explained earlier. So basically, this non-stationarity may compromise, as you see in the bullet up there. This is from FDOT, the operational characteristics of our project. And another interesting approach that I developed for this national, sea level rise report at the national level is, this curve. Let me explain what this is. You have a risk versus design life curve. So naturally, longer the design life, the more chances, even under stationary condition, for project to fail, if I want to call exceedance as a failure. So that is this black curve, this solid curve under stationarity. Longer the design life, the higher the risk. But under non-stationarity, which is shown in this highest curve or the red curve, is you have your risks are higher earlier in the with the for shorter design lives. So now the question is, maybe I can come up with a design that this will bring this risk down to the stationary risk. So I've come up with a way to determine what should my design quantile be, whether it's floods or sea level, how high my sea wall should be if I want to maintain a risk of about, let's say, 50%, which is equivalent to this, or it can be any lower risk. The point here is that this project with a bigger design, presumably because you like to have a smaller risk, will be more expensive. So it's a trade-off, what your level of protection you desire and how much you're willing to pay. And this is the risk formula that was used for this. And a slight modification of that would be now incorporating the damage functions, in terms of dollars and also vulnerability into one formula. So there is some work that has been done on this approach as well. So let me kind of go through one final concept here that I mentioned: adaptation solutions and pathways. Let me give you what I call this adaptation portfolio in our region. This is a whole bunch of solutions are being used for handling sea level rise and in general flooding and others. So basically, one of the things that we believe and we promote this idea of Everglades restoration, we basically will put more water into the Everglades that will benefit the urbanized areas because you get more seepage water into the area, and maybe we can mitigate some of the saltwater intrusion coming in from the ocean due to sea level rise. Other water conservation is obviously a no-brainer, low-hanging fruit. Water that you don't use is, basically you don't pay for, is the best water you can have. And then impoundment, temporarily store water during floods until the tides die down. So whole suite of solutions we have: green infrastructure, wastewater reuse, and others. So this is the kind of solutions that are being explored in our region to dealing with sea level rise and flooding, as I discussed earlier. And another example is forward pumping. Some of these gravity structures that were built and designed in the 50s, the Army Corps of Engineers did not think about sea level rise, so they are already under functioning. If you are in Miami, for example, the canals, certain times of the year, like right now, if there's a storm event, those structures at the end of those canals, they have to be closed twice a day during king tides because the sea level is higher than the interior canal. So this is where during those times, you have to have a pump station to pump out water. This is an example of a project north of Miami Airport. These are not cheap, these are expensive. That might be the long-term solution, like if you want to retrofit old infrastructure. And then obviously the natural infrastructure is preferred solution to mitigate storm surge flooding. So let me explain this dynamic adaptive policy pathways, which I really like and try to promote, and I hope you adopt this or embrace this concept. The reason we need to do this is the projections are highly uncertain. And this is, we know how to deal with uncertainty, but this is an area where the uncertainties are deep and you can't even put probabilities on them. So this is called DAP. And the whole idea is that basically decisions are made in dynamic interaction with the system. In other words, you watch the system, but the decision are made in time as we go along. In other words, we adapt incrementally, or you phase in your adaptation. So let me kind of explain that. The whole concept is you have different pathways. This phrase, different roads leading to Rome. In other words, you end up at the same location, but you may take different pathways to get there. We actually used this concept in a project in North Miami in Little River Basin. It's flooded a lot, as you can see on these pictures. So the question is, how do we implement this dynamic adaptation in this type of setting? We had a lot of data, digital elevation data, land use data, building polygons and all that, and some modeling. So this graphic shows the basic concept of dynamic adaptive pathways. This is, I think of a subway system in New York or Washington, D.C. You have basically different, like in a subway, you have rail lines, different colored, green line and the red line and the blue line. They are like our actions, action A, action B, action C, action D. And bottom is where the sea level rise rate might be shown. So at some point, if the sea level rise is higher, for example, this action B might stop working. It's not good anymore. You may have to go to a different pathway or different action, either to the red or the green or the blue. So the whole idea is you see a tipping point, you get ready when you approach the tipping point and you go to a different pathway. So this is very interesting in the sense that you look through the entire horizon and identify the pathways that you might need. But more importantly, you take steps to make sure you're not preempted using from a different pathway in the future. A good example, if you need the land to build a bigger pump station in the future, you make sure that land is not developed by developers or somebody else. So you think through those different pathways and you compare the cost and benefits and so forth. So in this example I mentioned, we had different portfolios, no action portfolio, a local flood mitigation or small pumps or regional pumps. And finally, the eventual solution have to be like in the Netherlands or other places, you may have to elevate the roads and houses. The point is you don't do this last option right away. You kind of take the steps to get there. And this pathway strategy tells you when to switch to one of these other solutions. So that's the whole concept behind this approach. And in that case, we use the expected annual damage for different portfolio or measures as a way to understand the tipping point. For example, in this case, when the sea level rise is 0.55 feet, in the M1 will stop working in terms of annual damage, and you may have to go to one of the other solutions like M3 and so forth. So this is a solution that we provided. There's a report on that if you're interested in looking at it. I'll be happy to share that with you. And finally, I want to communicate this concept called resilience principle. So this is something from the Dutch that we work together. I like these 5 principles. One is you adopt a systems approach. In other words, you don't look at your project in isolation. You look at the socio-economic system in the entire area in terms of a systems approach. The second is you need to think about beyond design events. In other words, we know we might have bigger events later, like we saw in Hurricane Ian last few days. So you need to look at those events as well. And more importantly, make sure infrastructure remain functioning even after the first exceedance. Like, this is where I mentioned, you make sure you design so that it can sustain exceedance like 2 or 3 times within the lifetime, for example. That could lessen the cost and increase the recovery capacity and make sure you remain resilient into the future. With that, I think we have about 15 minutes or less than, a little bit less than that. If you have any questions, and my favorite closing slide, what could happen in a sea level rise scenario. Anyway, with that, I'll be happy to answer any questions or entertain